start the part 2 of lecture 4 of real analysis. And even though on a YouTube channel I want to get views, I can show you another way on how to get notes. I feel like this is a bit weird. Where's lecture 4? Oh yeah, so it starts with ordered fields, the second part. Okay, but first I'll show you this. MIT.ocv.w, you can download. If you go to lecture notes for real analysis, you can see this entire lecture notes, and these are all the lecture notes. So we can look at, let's look at the part we've already gone to. We see the field. Shoot, they didn't even have that. What? Oh, they didn't even have the proof. See, these notes are lacking a bit. These don't have the proof, but hey, they have the same stuff over here. Oh, that's why Z is not a field. Simple properties follow from the properties of a field. Oh yeah, this was the actual proof. Ordered field. Oh shoot, that's the ordered field definition. And then we can see all of these, sequence 6, lecture 7. So if you want very nice notes, then I guess you can start watching my videos because I suck. Anyway, but those notes are pretty good, but you're missing out some stuff, so that's the reason you should watch this. Also, I really want views, okay, please? Everyone YouTuber wants views. And I don't care about likes again, you know that. Likes just suck. An ordered field is a field F, which is also an ordered set, such that, so it's an ordered set, and an order is a field F, which is also an ordered set. And there are two properties, and these properties again are not too hard. For all x, y, z, and f, if x is less than y, x plus z is less than y plus z. And the reason, when you saw in the previous lecture how I showed you that this doesn't work with that, and the reason is, well, first of all, only two numbers. Let's go 0, 1, 2. Okay? So 2 plus 1 is 0 in this situation. But 2 and 1 plus 1 is 2. How can 1 plus 1 be bigger than 2 plus 1? Even though 2 is greater. Huh? See, it doesn't work. See, this is what the finite sets lack. So this is basically easy. And then second one is also a pretty easy property. If x is greater than 0 and y is greater than 0, then x times y is greater than 0. I think this Z2 satisfies that, but these are both important properties. And now, a very simple idea you probably already know. If x is greater than 0, it's positive. And if x is greater than or equal to 0, it's non-negative, so it's not negative. It's positive and 0. Non-positive is the same thing. You could probably already guess what non-positive is going to look like, which is why he didn't mention it. The lecture. It's a he. Yeah. Oh yeah, and this is negative, by the way. So here's negative. So these are all the 4 terms you might hear in describing a number. So now an example is the rational numbers. The funny thing is, in these lectures, we've been trying to establish the real numbers from the. It's actually not that funny, but the real numbers and the rational numbers. We've been trying to move them apart. So this property is satisfied by both this and this. Obviously, it's R as well, because that's literally in its definition. If you remember what emojis, no emojis required. It's literally in its definition. So I'll get an example as well. And in fact, probably even the complex numbers as well, probably. I'm not sure about complex numbers. Pretty sure they are. And non-examples, as we see, I already told you. But now, no finite ordered sets. So no finite ordered sets. So theorem, this is a very basic theorem. If f is an ordered field, then if x is greater than 0, yes, x is in f. Just no for all, just x is in f. If x is greater than 0, it doesn't have to be. So if x is greater than 0, then negative x is less than 0. Same vice versa. You flip the inequality. And again, if it's 0, nothing really matters. So, and now this is a very elementary theorem, and we prove it. If x is greater than 0, this implies negative x plus 0 greater than is less than negative x plus x, which I don't really have to look at my notes now. This is plus 0 is less than, because of one of the properties. So by A4, A5, these two lines, negative x, is less than 0. That was a very easy proof, not too hard. So, side note, I don't know why I have the side note here. Let's see. So greatest lower bound property is satisfied if it has LUBP. So if this is satisfied, this is satisfied. If this is satisfied, this is satisfied. Anyway, so theorem. So So let f be an ordered field with the least upper bound property. Then if a is a subset of f and bounded below, then if a is an f. Wait, isn't this like a proof of like the greatest lower bound and how to satisfied on the least lower bound? Yes, this is literally the greatest lower bound property. If A is a subset of f and bounded below, and if f has the LUBP, it doesn't even have to have the greatest lower bound property. Saying if it has the LUBP, even the greatest lower bound property will be satisfied. F is an ordered field, by the way. F is an ordered field. Oh yeah, that's there. Okay. Suppose A is a subset of F, where A is non-empty. Oh yeah, I forgot it. Even in the proof it said A is even the theorem said non-empty. It's non-empty. A is bounded below. Then there exists a B in F such that for all A and A, B is less than or equal to A. Denote negative A as denote minus A as negative A for all A and A. So basically you multiply everything with negative 1. You could just do negative 1A because that's defined in the next lesson. Then for all A and A, B less than or equal to A, and for all A and A, negative A is less than or equal to B. You see how we switched the sign there? Negative B, which means B is an upper bound for negative A. There exists an X an F. I can barely see that. An F such that X equals to the supernum of A. God, this is getting annoying. Negative A. My least upper bound property. Then for all A and big A, negative A is less than or equal to X. Applies for all A and A, negative X is less than or equal to A. Which means negative X is a lower bound. And then now we will show y is a lower bound for A. Y is less than or equal to X. Will y be a lower bound for A? What? Then negative y is an upper bound for negative A, which implies X is less than or equal to negative y. Which means X equals to suit negative A, which means y equal to negative X, thus inf A equals to sup negative A. That was actually what we were trying to prove. And the same thing comes after the same. Now we're going to go on to the real numbers, discussion of the real numbers. So, there exists a unique ordered field with the least upper bound property containing the rationals. This field we denote by R. We won't prove this at all. It's a bit complicated. But what we will prove is this final theorem. There exists a unique element R in R such that R is greater than 0 and R squared equals to 2. You guys are thinking, hey, is it going to be like, yeah, basically, it's going to be that. But so now, sign out here. There's going to be some pretty weird stuff with this random thing on the top. This is tilde. Welcome, tilde. E tilde. We're going to see E tilde in this proof. And we'll also see R tilde. Oh yeah, on this proof we'll also see little R tilde. Nice. So let E tilde, I don't know, why did I put this? Let E tilde equal to x in the reals. X is greater than 0 and x squared is less than 2. So it's less than 2 right now. Then E tilde is bounded above too, so sup E tilde exists in the reals because of the least upper bound. Label R equals to sup E. Then the same proof, I think we skipped it, shows that R is greater than 1 and R squared equals to 2. I think we skipped it. Did we do this? So now we've gotten to this point. So R is sup E tilde. So R is greater than 1 and R squared is equals to 2. So we now prove R is unique. Suppose R tilde is an R. R tilde is or equals to R. I don't know. R tilde is greater than 0 and R tilde equals to 2. Then 0 equals to R tilde squared minus R squared. So R tilde is greater than 0, right? So, and R tilde, wait, does that say greater than, R tilde squared is greater than or equal to 0, sorry. So that is greater than, not greater than or equal to, greater than 2. So obviously 0 equals what? Oh, it's equal only. So R tilde minus R squared, which equals to R tilde plus R tilde minus R which means R equals to R tilde. There is only one. You can also show 3 to exist in R, and generally if x is in R, x 1 to the n exists in R if okay, so we're done with lecture 4, everyone. So goodbye, and also lecture 5 is going to go a bit crazy about the Archimedean property density of the rationals. So it's going to be a bit complicated. So bye everyone.